deep in the silence between stars, where no human ear has ever heard a sound, something vast is moving toward us. It is 7 miles across, a mountain of ancient ice that predates our planet, and it races through the black at velocities that mock the limits of our imagination. Astronomers have named it 3I Atlas, the third confirmed visitor from another star. Yet its trajectory is so uncanny, so improbable, that it has raised a question older than science fiction itself. What if this is not a mere fragment of interstellar debris, but a deliberate emissary? The path it traces reads like a script of reconnaissance. First Mars, then the hidden arc behind the Sun, a near approach to Earth, and finally a plunge through the magnetic fortress of Jupiter, each stop an opportunity to observe, to measure, to listen. For centuries, we have told ourselves that visitors from other stars would be blind rocks, ice shards, cosmic refuse hurled across the galaxy by gravity's indifferent hand. But what if we were wrong? What if some are not wanderers at all, but scouts machines dressed in the camouflage of comets, dispatched by civilizations long since vanished into the darkness, civilizations that learned to hide? This is the unsettling promise of the so-called Black Forest theory, that the galaxy teems with intelligent life, but it is cautious, fearful, and concealed. In that forest, survival belongs to those who mask their presence, deploying probes disguised as natural objects. Such probes would drift into young star systems, sampling their atmospheres, recording their signals, noting whether a species has climbed high enough to glimpse them. And here, now, we find 3I Atlas, an object whose motions look less like accident and more like choreography, a grand tour that maximizes surveillance while never revealing intent. Unlike the enigmatic ʻOumuamua, unlike the cometary Borisov, Atlas seems almost designed to play the role of ghostly visitor, perfectly ordinary at first glance, perfectly camouflaged. The stakes are stark. Either we are witnessing humanity's first contact with extraterrestrial technology, or we have stumbled upon a coincidence so extreme it seems to mock probability itself. To judge, we must return to the beginning, to the moment this icy wanderer first revealed itself to our instruments. The discovery was not cinematic. There was no flash of light or sudden alarm. Instead, it was the quiet patience of machines. On the 1st of July, 2025, at the Atlas Observatory in Rio Hurtado, Chile, a faint point of light moved slowly against the starfield. Its first name was not 3I Atlas, but the provisional A11PI3Z, one more alphanumeric code in the endless bookkeeping of the sky. Nothing in that string of letters hinted at cosmic drama. Atlas, the asteroid terrestrial impact last alert system, was never built to find alien probes. Funded by NASA and operated by the University of Hawaii, its mission is to protect Earth. 4 telescopes, spread across the globe, each sweep the heavens every clear night. Their task is to find killers, the asteroids that could one day strike our world. Yet in watching for threats, they are also exquisitely sensitive to the unusual, the unexpected, the interstellar. The Chilean Discovery Telescope, half a meter wide, armed with CCD cameras of extraordinary sensitivity, flagged A11PI3Z for follow-up. Nothing unusual so far. Every night, the system catalogues thousands of moving lights, main, belt asteroids, near-Earth objects, comets returning on long ellipses. At first, this one looked ordinary too. Its brightness was feeble, magnitude 19, utterly invisible to the unaided eye, faint even for amateur instruments. Its motion was slow, a crawl across the star field that spoke of great distance. But the algorithms did not discard it. Something in its trajectory called for more attention. In astronomy, the key to unmasking an interstellar traveler lies in a single number, orbital eccentricity. Any object bound to the Sun must have eccentricity less than 1, tracing closed ellipses like obedient planets. But an eccentricity greater than 1 signals freedom. A hyperbolic arc, a brief trespass through our system before vanishing back into the galaxy forever. The first calculations on ʻOumuamua hinted at such a number, yet caution ruled. Measurements from a single night are treacherous. Turbulence in the air, imperfections in the detectors, the faintness of the signal all can distort the orbit. Astronomers have learned to be wary. Many times before, promising candidates proved to be comets bound to the Sun, their orbits stretched but still closed. The test, then, was repetition. Within days, telescopes around the world joined the hunt. In Tenerife, the European Space Agency's optical ground station tracked the faint traveler, confirming the hyperbolic suspicion. In Arizona, the Catalina Sky Survey added more points of light to the growing arc. Each observation shrank the error bars. Each night tightened the truth. By the 6th of July, the case was unassailable. Eccentricity greater than 1, confirmed across independent sites, converging on certainty. This was not ours. This was the third interstellar object ever detected. The machinery of astronomy moved swiftly. The International Astronomical Union's Minor Planet Center, keeper of the solar system's census, assigned it the formal code C divided by 2025 N1, Atlas. The C marked its cometary appearance, the N1 its place in the calendar. First discovery of the second half of July. Then came the simpler name that the public would remember, 3I. Atlas, the third interstellar. Oumuamua had been the first, Borisov the second, and now this. The response within the community was electric. Oumuamua had taken us by surprise in 2017, spotted only as it fled. Borisov in 2019 had been a more ordinary comet, yet still a wonder for its alien chemistry. Now came Atlas, announced in real time, while still inbound, offering months of scrutiny. Years of preparation had not been wasted. Protocols for rapid response had been drafted. Telescopes had been primed. Theoretical papers had speculated on the possible. Funding streams had been set aside for exactly this moment. Among those watching was Dr. Robert Werrick, the astronomer who had first flagged Oumuamua. He noted the strange duality. The process was familiar, the painstaking confirmation, the designation rituals, but the object itself promised something different. Oumuamua had been a fleeting ghost, already vanishing when we noticed it. Atlas was a visitor still arriving, a messenger not yet at perigee. The sky had handed us a chance not to miss, and so the stage was set. A frozen relic from the birth of another star system, or a disguised machine sent to watch us from the shadows. The faint speck of light, magnitude 19, had become a mirror for our greatest hopes and fears. It is coming still, tracing its improbable reconnaissance arc through our system. To the patient eyes of telescopes, it is nothing more than photons across CCD chips. To us, it may be the threshold of a larger universe, one no longer silent, one no longer empty. The challenge of observing 3I Atlas was immense, but not insurmountable. When it was first noticed, the object lay 5.2 astronomical units from the Sun, roughly the orbit of Jupiter, receiving only a whisper of solar warmth. At that distance, any cometary outgassing would be muted, its activity subdued, nearly invisible. Astronomers knew the real spectacle would come later, on the 29th of October, when it would sweep through perihelion at 1.36 AU, sunlight striking it with far greater intensity. As anticipation grew, professional observatories around the world began reshaping their schedules around this cosmic guest. The Hubble Space Telescope reserved precious director's discretionary time, while the James Webb prepared infrared spectroscopy to peel back the chemical story of its ice. On Earth, telescopes from Chile to Hawaii cleared their calendars, and even amateur astronomers joined in the vigil. Philip Romanov, working remotely through a half-meter telescope in Chile, captured one of the first independent confirmation images just a day after discovery. His picture was unassuming, a faint smear against a crowded star field. Yet within that blur lay a profound truth. It was humanity's first photograph of a new visitor from the deep between stars. By mid-July, the first flush of excitement gave way to organized campaigns. What had begun as a chance detection was now the focus of one of the most intensive observational efforts in the history of astronomy. The early data hinted at something unprecedented. This was not merely another interstellar traveler. Its sheer size set it apart. Photometric analysis measuring light curves across nights of tracking suggested a diameter of 11 kilometers, 7 miles across. For astronomers, the revelation was staggering. ʻOumuamua, the first interstellar object ever identified, had been a thin shard, perhaps 400 meters long, no wider than 40 meters across, strange in shape, but modest in scale. Borisov, the second, had been even smaller, a comet with a nucleus less than a kilometer wide. Against these, Atlas loomed like a giant, 1,000 times the volume of ʻOumuamua, perhaps 10,000 times the mass. Suddenly, the paradigm shifted. Such enormity carried consequences. A sliver like ʻOumuamua could be explained as the byproduct of planet formation, a fragment flung loose during gravitational chaos. Borisov, too, could be slotted neatly into that narrative. But an object as massive as Atlas required more dramatic origins. Perhaps it was the core of a shattered dwarf planet, hurled away by catastrophe. Perhaps the remnant of a moon flung outward by gravitational tides, or the wreckage of a massive comet torn apart. Its size was also its armor. Interstellar space is not empty but strewn with dust grains, bombarded by cosmic rays, scoured by charged particles. Over millions of years, small bodies erode to nothing, sublimating into invisibility. But a 7-mile giant endures. It carries enough mass, enough internal cohesion, to survive the voyage between suns almost indefinitely. The implications deepened. Such a bulk could hold onto its ices through ages. Smaller bodies, exposed to vacuum, quickly lose their volatiles. The ratio of surface to interior works against them, allowing sublimation to hollow them out. But Atlas, with its volume dwarfing its exposed surface, could shelter primordial ice, organics, and carbon compounds at its core for billions of years. It was a time capsule from another system, a frozen archive predating Earth's own oceans, sealed against the ravages of interstellar exile. Astronomers turned to light curves to probe its shape. As Atlas rotated, its brightness flickered in a slow rhythm. Analysis suggested a rotation period of 12.4 hours, half an Earth day. Unlike ʻOumuamua, whose brightness swings betrayed a stretched needle-like form, Atlas showed only gentle variation. The conclusion was striking. It was roughly spherical. This mattered. Elongated forms imply violence, tidal shredding, collisions, or even some whispered, artificial manufacture. Spheres, by contrast, are the hallmark of accretion, of matter gathering under gravity until it rounds itself. In this way, Atlas seemed to echo the familiar story of planets, moons, and comets in our own system. Its surface properties offered more clues. The albedo, the fraction of sunlight it reflected, was measured at just 0.04. In other words, only 4% of light bounced back. It was darker than charcoal, blacker than ash. This is the hallmark of cometary nuclei, crusted with complex organics and carbon-rich minerals, a coating that drinks in sunlight rather than gleams. This darkness stood in stark contrast to ʻOumuamua, whose unusually high reflectivity had raised suspicions about its true nature. In this, Atlas seemed more natural, more typical, yet all the more powerful as a counterpoint. Estimating its mass required leaps of inference. At such distances, gravitational tug on other bodies was imperceptible. There was nothing to measure directly. Instead, astronomers assumed density, guided by spectroscopy. The signatures hinted at a mixture of water, ice, and silicate rock, not unlike comets at the edge of our own solar system. From this, they derived an astonishing figure: 1.2 trillion kilograms, the weight of a mountain transposed into the sky. That mass, so immense yet so delicately balanced in the void, underscored the object's potential role as a preserved relic. Within it might lie molecules unaltered since the birth of its home star, molecules that could tell stories about chemistry at the dawn of worlds. Each measurement, each refinement of data, only sharpened the paradox. In scale and survival, Atlas behaved like the most robust example of interstellar detritus ever seen. Yet in path and choreography, it moved as though following a plan. Was this, then, the archetype, the natural standard for interstellar objects? Or was it the exception, the one whose strangeness would redefine the rest? Observers braced for answers. With perihelion still ahead, and with instruments poised to capture every photon it shed, Atlas had become more than a curiosity. It had become a crucible for our deepest question: are we seeing chance or intention? And as it turned in the darkness, slowly, every half-day, the mystery only grew. Unlike its smaller, more fragile predecessors, 3I Atlas carried within it the promise of untouched history. Where ʻOumuamua and Borisov may have been shards, weathered fragments of larger bodies, Atlas appeared to be something more complete, a capsule of primordial matter, ice and minerals that had never known the heat of a star. Density estimates, drawn from the marriage of mass and volume, yielded a surprising figure: just 0.6 grams per cubic centimeter, lighter than solid rock, yet perfectly consistent with a mixture of water, ice, organics, and silicate dust. This was the density of comets, the frozen giants born in the outer shadows of planetary systems, far enough from their suns for ices to condense, unscathed by warmth. By late July and into August 2025, a picture was coming into focus. Atlas was no ordinary interloper, but a pristine survivor of a protoplanetary nursery beyond our own. Its size, its roundness, its low density all pointed to slow accretion in the cold hinterlands of a long-lost solar system, and ejection by the gravitational hand of giant planets. Yet even these sober conclusions, reassuring in their familiarity, were only the prelude. For as telescopes sharpened their gaze, what began to emerge would strain the comfort of simple explanations. The scale of Atlas alone was transformative. ʻOumuamua had been an enigma too small to interrogate deeply. Borisov, a comet too insubstantial to linger under scrutiny. But Atlas was different. For the first time, astronomers had in their reach an interstellar object large enough to yield real detail: composition, chemistry, isotopes, spin. In its bulk lay the possibility of new models of planetary genesis and, perhaps, insights into the distribution of life's raw ingredients across the galaxy. The summer of 2025 became a feverish race to extract as much information as possible before this rare visitor slipped back into the dark. The first breakthrough arrived from the NASA Infrared Telescope facility atop Mauna Kea. Its spectrometers traced the fingerprints of water ice, shimmering across multiple infrared bands. Water was expected. Our own comets are brimming with it. But here the water carried a signature that electrified the field. In the ratios of deuterium to hydrogen, scientists read a story older than Earth itself. The numbers did not match terrestrial oceans, nor Kuiper Belt comets, nor the ancient meteorites that fall to our deserts. This was water unlike any in our solar system, its isotopic balance whispering of an alien nursery, of condensation in a place with different stellar chemistry, perhaps 7 billion years in the past. In that instant, astronomers realized what they held. Our oceans, our ice, our comets, all have been baked and remade by billions of years of thermal cycling, of collisions and heating. The water of Atlas, by contrast, was unaltered since birth, a fossil liquid, frozen in place since its parent star's disk collapsed. No heating, no processing, a direct sample of the galaxy's deep memory. Gemini South in Chile soon added its voice. Through its spectroscopic eyes came the signatures of organics, methane, ethane, and more complex carbon chains. Alongside the water lay hydrocarbons, stable and volatile, formed in a chemistry both familiar and strange. There were heavier organics too, polymers, kerogen-like compounds, materials that on Earth we associate with biology, though in space they can emerge through the alchemy of radiation and time. Their isotopes told still more. These molecules had formed in an oxygen-rich environment, unlike our own solar system, where carbon often rivals oxygen in abundance. That suggested a parent star older, perhaps more evolved, one that had already seeded its nursery with multiple generations of heavy elements. Layer by layer, the story grew stranger. Carbon-rich minerals appeared, but without the thermal scars of migration. Solar system comets often betray the fingerprints of high-temperature minerals, fragments of rock that once orbited close to the young sun before being scattered outward. Atlas showed none of these. Its spectrum was pure cold chemistry, condensed at temperatures near 30 Kelvin, just 30 degrees above absolute zero. It had not gathered material from inner zones. It had formed in situ, far out in the frozen rim of its home system. To astronomers, this was astonishing. Here was matter untouched by fire, a fragment of disk material frozen at the edge of another world's solar birth. For the first time, we could test our models against reality, not simulations, not guesses, but the physical truth of another star's nursery. The implications rippled outward. If Atlas carried such molecules, what did that say about the diversity of chemical environments in which planets are born? How common are organics in alien disks? How often does water condense with such isotopic quirks? And deeper still lay the possibility that made the hairs rise on the back of every neck. What if this chemistry was not only natural? On Earth, carbon polymers, organics, kerogen, all of these are linked to life's activity. In the void, they can form abiotically, certainly. Yet the isotopic peculiarities hinted at environments rich, oxygen-heavy, stirred by generations of stars before, conditions fertile, at least, for something more. As the weeks of 2025 wore on, Atlas became less an object and more a revelation. It was the first true probe into the galaxy's laboratory of worlds, a chance to test our ideas about how planets assemble, how disks evolve, how chemistry spreads. It was also a mirror, reflecting back the profound question we still do not dare to answer. Are we looking at an accident or a message? Is this a comet or a capsule? Whatever the truth, the pristine body of 3I Atlas, blacker than charcoal, colder than deep space, and older than Earth, had become a frontier. Through its light, we were touching a place we could never visit, and through its chemistry, we were reading the early sentences of a story that might one day include us. 3I. Atlas became more than a curiosity. It transformed into a laboratory in motion, carrying with it the chemistry of another world. By examining its ices and minerals, astronomers could probe how stellar metallicity, disk temperatures, and the architecture of protoplanetary nurseries shape the raw ingredients of planets. The discovery of complex organic molecules carried implications that extended far beyond mineralogy. These organics could form abiotically, yes, through the patient chemistry of radiation and simple precursors. But their survival within an untouched interstellar body proved something profound. Life's essential scaffolding can emerge naturally, and it can endure across billions of years, carried star to star in the vault of space. In this, 3I Atlas seemed to whisper that organic chemistry is not a rarity, but a galactic inevitability. As August 2025 unfolded, more details surfaced. Trace elements within its ices pointed toward formation around a star with metallicity nearly 1/3 higher than our Sun's, a star older by perhaps 2 billion years. Its advanced age could account for the unusual isotopic patterns, the abundance of complex organics, and the heavy element enrichments. Nitrogen isotopes added more texture. The ratio of nitrogen 1,4 to nitrogen 1,5 bore the fingerprints of nucleosynthetic pathways alien to our solar heritage. Such isotopic markers hinted that one day we might be able to trace Atlas back to its parent star, to locate the ancient nursery where its story began. Even more astonishing was what the analysis did times not times show. Despite what may have been eons adrift in the interstellar gulf bombarded by cosmic rays, bathed in the magnetic tides of the galaxy, colliding with dust and particles, Atlas carried almost no evidence of alteration. Its outer shell had shielded its core with remarkable efficiency, keeping its interior chemistry essentially frozen in time. The possibility lingered that perhaps its journey through the void was shorter than assumed, or perhaps its sheer mass had preserved it with unrivaled fidelity. Whatever the explanation, the preservation of primordial chemistry in such an ancient object was nothing less than a gift. For the first time, humanity could study the untouched materials of another stellar system, preserved across cosmic epochs. It was a time capsule in ice and stone, a vessel of planetary memory. Yet even as its chemical portrait sharpened, subtle inconsistencies crept into the narrative. Observers began to note anomalies, slight deviations that resisted easy explanation. They did not overturn the cometry model outright, but they seeded unease, as though the object's story were layered with something more complex. And then came the orbital data. Astronomers refined their calculations, plotting its entry path with increasing precision. At first, nothing unusual. A steep retrograde orbit opposite the planet's march around the Sunday. Such retrograde arrivals are not surprising for interstellar bodies, which can come from any direction. But as the numbers converged, a pattern emerged that felt less like randomness and more like choreography. Its orbital plane was tilted 162 degrees relative to Earth's nearly polar retrograde orbit. By coincidence, or by design, this tilt meant the object would remain visible to Earth-based telescopes throughout its passage, never vanishing behind the Sun for long stretches as most objects do. It was as though its path had been tailored for maximum watchability. Then came the encounters. The 3rd of October, 2025. A pass just 18 million miles from Mars, close enough for spacecraft in orbit to study its coma and tail, as dawn broke across the Martian sky. The 29th of October, perihelion, at 1.36 AU, grazing just outside Earth's orbit. The geometry ensured maximum solar heating while avoiding destabilizing gravitational kicks. From Earth, the Sun would block direct views, but spacecraft stationed at L1 or Mars orbit would have the vantage. The 19th of December, 2025, the object would drift 170 million miles from Earth, a sweet spot far enough to avoid interaction, close enough for the Webb and the Rubin Observatory to capture it in exquisite detail. And then, the crescendo. The 16th of March, 2026. Atlas would sweep just 33 million miles above Jupiter's cloud tops, plunging into its vast magnetosphere. The trajectory would carry it through Jupiter's magnetotail, a region alive with charged particles, dust, and plasma, perfect conditions for spacecraft like Juno to sample the material shed by the interstellar body. It was a rendezvous so unlikely it seemed written. Statistical analysis confirmed the strangeness. The inclination's alignment with Earth's observational window had less than a 0.2% chance of happening at random. Factoring in the specific planetary encounters, the timing, the distances, the overall probability shrank to 1 in 20,000. Small odds, but significant enough that sober astronomers began to whisper about non-random explanations. The trajectory, seen in this light, resembled not accident but reconnaissance. Mars for geological observation, perihelion for solar calibration, Earth for line-of-sight visibility, Jupiter for magnetospheric sampling, each step an opportunity, each encounter efficient. The path would have been difficult to improve upon even if designed intentionally, as though by some intelligence intent on surveying the solar system while cloaked in the guise of a comet. There was camouflage too. Periods when it would slip behind the Sun relative to Earth, moments of maximum distance, when detection would be most difficult, natural concealments written into orbital mechanics. And yet, always, the alignment ensured we would never fully lose it from sight. The paradox deepened, hidden, yet not hidden. Its speed added another layer. Atlas approached at 33 kilometers per second relative to the Sunday. This velocity exceeded what would be expected from bodies ejected by nearby stars. It hinted at an origin from farther afield, beyond the local neighborhood, flung from regions where the gravitational web of the Milky Way imparts more extreme energies. Each calculation, each refinement, only amplified the tension. Was this a natural marvel, a cometary behemoth on a miraculous trajectory? Or was it, as some dared to murmur, an emissary in disguise, following a path scripted not by chance but by intention? 3. Atlas cut through the void, like a message we were only beginning to decipher. The velocity of 3-1 Atlas is itself a riddle. At 33 kilometers per second relative to the Sun, it arrives faster than objects typically flung from nearby stars. Such speed implies either an origin far beyond our stellar neighborhood or, unsettlingly, an artificial acceleration beyond what natural gravity assists could provide. Its retrograde orbit adds another layer. Moving against the grain of planetary motion, Atlas collides head-on with the streams of dust, charged particles, and solar debris that flow through the inner system. In doing so, it samples a far richer flux of material than any prograde traveler could. For a natural comet, this is coincidence. For a probe, it would be design. Gravitational modeling reveals still more peculiarities. In its long approach, Atlas threads a path that neatly sidesteps the outer giants. Saturn, Uranus, Neptune, all positioned such that their pulls are minimized, leaving its trajectory unperturbed until it enters the realm of Mars, Earth, and Jupiter. To many, this looks deliberate, a careful choreography to preserve the integrity of its encounters with the inner system. The resemblance to trajectories calculated by NASA and ESA for hypothetical interstellar missions is striking. In white papers and simulations, engineers have charted optimal paths for probes venturing to nearby stars, and the similarities to Atlas's route are difficult to ignore. Interstellar navigation is notoriously unforgiving. A traveler must account for stellar drift, galactic rotation, the tug of hidden masses, the tide of the Milky Way itself. To carve a path as precise as Atlas's would demand either staggering luck or a guiding intelligence. Skeptics urge caution. They remind us of confirmation bias, the human impulse to inscribe patterns into randomness. Billions of objects, countless trajectories, unlikely events are inevitable given enough chances. But the probabilities here are not trivial. The inclination aligning with Earth's observational window, the sequence of planetary flybys, the survival of coherence across light years, all of it together suggests a choreography we struggle to call chance. What no one disputes is that Atlas's journey through our solar system is among the most precise celestial ballets ever recorded. Its milestones are set like acts in a play, each one a stage for new revelations. The 3rd of October, 2025, the Mars flyby. Atlas sweeps within 18 million miles of Mars, closer than any previous interstellar object has come. It arrives at Martian dawn, the red planet's horizon still shadowed while the object glows against a dark sky. Spacecraft in orbit: NASA's MAVEN, ESA's Mars Express, China's Tianwen-1 will have perfect lines of sight. MAVEN's instruments, designed to taste Mars's tenuous upper atmosphere, will instead sniff for any gases the interstellar body sheds. Mars Express will sharpen its cameras on the faint smudge, while Tianwen-1 provides a triangulated view. Even the rovers, Perseverance and Curiosity, might glimpse it if the thin skies clear. The timing is exquisite. Atlas is still inbound, still far from the sun's heat. Should a coma or tail appear at this distance, it would defy expectations, suggesting either unusual chemistry or something stranger: controlled venting, engineered outgassing. At 7 miles across, Atlas will appear as a disk in high-resolution imaging, not a point of light. Its surface, its spin, even asymmetries in emission might be revealed. The 29th of October, 2025, perihelion. Here lies the climax. Atlas plunges to 1.36 AU, just outside Earth's orbit, the sun flooding it with heat. Temperatures rise, volatiles should erupt, a coma should bloom. Its velocity peaks at 152,000 miles per hour. Yet from Earth, we are blind. The sun's glare hides it, concealing the most critical moment. Only spacecraft at the L1 Lagrange point SOHO, South Dakota O, will have eyes, their coronagraphs blocking the sun's blinding disk to reveal the visitor against the corona. Mars, fortuitously aligned, will stand as our proxy witness. From orbiters circling the red planet, the object will be visible as it reaches its most vulnerable state. For natural comets, perihelion is predictable: maximum outgassing, long streaming tails. But if Atlas resists, if its surface remains strangely quiet, or if it emits in patterns inconsistent with sublimation, then something unprecedented will have been revealed. Solar heating will also be merciless. If there are artificial structures within, they may fracture, vaporize, or betray themselves in anomalous spectra. In this crucible of fire, nature and artifice may finally diverge. The 19th of December, 2025, Earth observation window. Having rounded the sun, Atlas swings outward, passing 170 million miles from Earth beyond Mars's orbit, but still within reach of our greatest telescopes. For the first time since perihelion, terrestrial observatories regain their quarry. The James Webb Space Telescope, the Vera C. Rubin Observatory, and Earth's largest mirrors will probe its surface and composition anew. This will be the moment to compare. What has changed since its solar trial? Did volatiles erupt as expected? Has the body fractured, brightened, dimmed? Any deviation will sharpen our theories, either reaffirming its nature as a giant comet or pushing us further into the realm of speculation. And beyond, the journey continues. Toward Jupiter, toward its magnetosphere, toward encounters so uncanny they already feel mythic. Each step has been laid with mathematical elegance, each milestone like a breadcrumb on a trail through our system. Whether by chance or design, 3I Atlas carries us into territory where astronomy and philosophy blur. It is at once a comet, a probe, a messenger, a mirror. What it truly is will be written not only in its chemistry or trajectory, but in what we choose to see when the improbable arrives at our doorstep. The James Webb Space Telescope will stand at the heart of the campaign to decode 3I Atlas, its unmatched infrared sensitivity, peeling back the chemistry of whatever coma or tail the object may unfurl. JWST's spectrometers can taste gases at concentrations invisible to Earth-bound instruments, tracing isotopic fingerprints, even sniffing for exotic volatiles that might hint at something unnatural. Meanwhile, the Vera C. Rubin Observatory with its immense 8.4-meter mirror and revolutionary camera array will chronicle the subtle dance of brightness and color, watching for faint flickers that might betray activity, surface shifts, or structural change. This December window is pivotal. Atlas will be slicing through the solar plane, immersed in solar wind and dust streams, an ideal moment if, hypothetically, it carried mechanisms to sample material from our star system. Across the radio spectrum, another kind of vigil will unfold. Ground-based dishes will lock on, listening not for natural spectra, but for whispers, regularities in electromagnetic noise, the faint murmur of active systems. At 170 million miles, Atlas will be close enough for signals to carry, yet far enough to avoid drowning in the sun's radio roar. But the greatest stage comes on the 16th of March, 2026, above Jupiter. Atlas will swing just 33 million miles from the giant's cloud tops, well inside the reach of Jupiter's sprawling magnetosphere. Here, the opportunity is unprecedented. NASA's Juno, circling the gas giant, will be perfectly placed. Its instruments, designed to probe Jupiter's interior and magnetic field, will instead watch the interaction between interstellar ice and the most powerful magnetosphere in the solar system. Radiation will roar through Atlas, charged particles lashing its surface. A natural body would respond predictably, volatiles streaming, ions sputtering. An artificial system would need shielding, engineering. Differences, perhaps, could be seen. There is the chance, too, of something historic. Juno's detectors may capture dust grains flung from Atlas, particles seized by Jupiter's magnetic field and funneled past the spacecraft. If so, humanity would hold, for the first time, direct samples of matter born around another star. More, the gravity of Jupiter itself offers a final gift, a weighing scale. By tracking how Atlas's trajectory bends in response, astronomers will pin down its true mass, its density, its secrets of structure and survival. This flyby is the last grand act. After Jupiter, Atlas will slip outward, its hyperbolic arc carrying it beyond our reach. Its course will be tweaked by Jupiter's gravity, a final adjustment etched into its outbound path. Telescopes will follow as long as they can, perhaps into 2027, catching the dimming smudge until it vanishes back into the dark. Each observation approach, perihelion, Earth window, Jupiter Pass forms a chapter of an unrepeatable story. Yet, alongside the science rises the haunting question: is this choreography mere coincidence, or is it design? Atlas's journey is as carefully studied as its chemistry, and both raise questions that refuse easy answers. It is here that the dark forest theory enters, a hypothesis drawn not from data, but from fear and reason. Popularized by Liu Cixin in his three-body problem trilogy, it casts the universe as a wilderness, dense, silent, perilous. Every civilization is a hunter. To survive, it moves quietly among the trees. To make noise, to reveal oneself, is to invite annihilation. Silence becomes the law of existence. Detection, the mark of doom. The theory rests on four brutal premises. First, survival is the ultimate aim of any civilization. Second, no one can ever know the true intentions of another. Third, technology, once unleashed, will always march toward destructive capacity. And fourth, the distances of space render trust and negotiation impractical. Communication takes years, centuries. Intentions shift faster than signals arrive. A neighbor seen today as harmless may tomorrow wield weapons of system-wide destruction. In this logic, discovery equals danger. To see another civilization is to face a choice without solution. You cannot know if they are hostile. You cannot trust what they will become. You cannot talk quickly enough to be sure. The only safe move, the theory suggests, is a first strike swift, decisive, erasing the risk before it erases you. This is the dark forest strike, the cold arithmetic of survival in a galaxy where silence is life. If Atlas is natural, then it is simply the grandest comet ever gifted to us. If it is not, then perhaps it is something worse or something wondrous. A probe, disguised as stone, drifting silently by, a hunter's eye in the trees, measuring us, or a messenger, patient, ancient, carrying the chemistry of one world into the skies of another. Its trajectory, its size, its pristine ice, all are facts. What they mean remains the story we are writing now, as Atlas moves through our system, and as we debate whether the universe's silence is emptiness or strategy. The dark forest hypothesis paints the galaxy as a wilderness of silence, a cosmic standoff where survival depends on remaining unseen. In this vision, every civilization is a hunter creeping through the trees, acutely aware that to announce one's presence is to risk annihilation. Advanced species, if they exist, would cloak themselves in elaborate camouflage, watching the skies while never signaling. Each waits, hidden and fearful, hoping to glimpse another before being glimpsed themselves. The implications extend beyond abstract metaphor. Such civilizations would not rely solely on passive listening, but would scatter reconnaissance systems across the stars, probes, sensors, and monitoring stations disguised as nature itself. They would masquerade as comets, asteroids, even dust clouds, their technology hidden inside familiar shells. In this framework, 3I Atlas becomes not merely an oversized interstellar comet, but potentially an emissary cloaked as a watchful instrument moving quietly through our solar system. Its very scale takes on new meaning. A body 7 miles wide offers cavernous space to hide sensors, reactors, processors, an arsenal of observation systems sealed beneath an icy rind. Its immense mass doubles as protection, a radiation shield, a buffer against solar storms, insulation for electronics over journeys lasting millions of years. The trajectory, already improbable by natural standards, appears instead as tactical design. Each planetary flyby maximizes data gathering while minimizing conspicuousness. Perihelion arrives not when Earth-based telescopes can track it, but when it vanishes behind the Sun, creating a window of unobserved operations. Even its composition, pristine and alien, leaves room for doubt. If the object is natural, then its ices and organics are records of a star older than our own. But what if they are not? An advanced civilization could craft artificial ice, engineer isotopic ratios, manufacture organics that perfectly mimic the chemistry of ancient systems. To our instruments, it would look authentic. To their designers, it would be camouflage. In this scenario, the purpose of 3I Atlas becomes clear: reconnaissance. The probe would arrive to study our solar system comprehensively, its planets, its chemistry, and, above all, its inhabitants. It might be equipped to map Earth's atmosphere for industrial signatures, to eavesdrop on our radio chatter, to monitor satellites and spacecraft. Its passive sensors could operate silently, while more active systems might come alive only during concealment, such as when the Sun shields it from Earth's watchful telescopes. And then, once the survey is complete, it departs, vanishing back into interstellar space. Staying longer would increase the risk of detection, of mistakes, of exposure. A single sweep-through mission, by contrast, gathers intelligence efficiently while preserving cover. Critics remind us, however, that this interpretation leans heavily on human fears and assumptions. The dark forest framework presumes that all civilizations prioritize survival in the same way, that they develop technologies resembling our own, that they share our inclination toward preemption and secrecy. Alien intelligences may not think in our terms at all. Their psychologies, shaped by evolutionary pressures we cannot imagine, may not conform to our models of strategy or risk. The theory also struggles with scale. If a civilization can master interstellar travel, why would it fear a species as primitive as ours? Even if humanity someday poses a threat, such danger lies millennia away. Would beings capable of spanning the stars really waste effort surveilling a civilization that still clings to its home planet? And yet the theory remains seductive. It explains the Fermi paradox, the silence where we expect noise. It rationalizes why the galaxy appears empty, while probability insists it should be full, and it gives a coherent framework for anomalies like 3I Atlas, massive, pristine, and improbably precise in its path. Whether or not it is correct, it urges us to treat such objects with suspicion, to consider that natural may not always mean unthinking. It also forces us to confront the implications of our own behavior. Our radio transmissions, our satellites, our rockets, they are beacons in the forest. If the dark forest hypothesis holds true, then every broadcast we send, every rocket we launch, could be a flare in the night. Somewhere, hidden hunters may already be listening. Into this debate steps Dr. Avi Loeb, the Frank B. Baird Jr. Professor of Science at Harvard, perhaps the most controversial voice in modern astrophysics. Loeb has long urged the scientific community to consider hypotheses others dismiss. His notoriety grew with ʻOumuamua, the first interstellar visitor. That elongated body, accelerating mysteriously away from the Sun without visible outgassing, puzzled astronomers. Many proposed exotic ices or structural oddities to explain it. Loeb proposed something far bolder: artificial origin, a light sail propelled by radiation pressure. He laid out his case in Extraterrestrial, the first sign of intelligent life beyond Earth, igniting a firestorm. To some, he was a visionary, challenging the complacency of orthodoxy. To others, he was a respected scientist who had stepped too far into speculation. Regardless of where one stands, Loeb's influence is undeniable. His insistence on entertaining the possibility of intelligence, however uncomfortable, reoriented the conversation. In the case of 3I Atlas, his perspective resonates even more strongly. Here is an object not only larger and more pristine than Oumuamua, but one whose trajectory itself raises eyebrows. If ever there was a candidate for deliberate design, this might be it. The debate continues, poised between wonder and fear. Is 3I Atlas a relic, a probe, or a phantom coincidence? The dark forest warns us that silence is survival, that watchers hide in plain sight, that probes may masquerade as comets. And as we chart Atlas's path, as we measure its chemistry and mass, we cannot escape the possibility that it is watching us in return. With the arrival of 3I Atlas, Avi Loeb once again steps into the limelight, challenging the boundaries of what the scientific imagination dares to propose. In a paper co-authored with Dr. Carson Ezell of the Harvard-Smithsonian Center for Astrophysics, he argues that this colossal body exhibits traits that lean not toward natural origin, but toward technology masquerading as nature. His central claim is simple yet radical. At 7 miles in diameter, 3I Atlas sits in a Goldilocks zone of size large enough to conceal any imaginable instrumentation, yet still plausible as a natural cometary visitor. For Loeb, scale is more than a statistic, it is an advantage. Mass on this order offers superb radiation shielding, allowing sensitive electronics to endure million-year journeys between suns. The volume permits redundancy, power reserves, and systems that could last for geological epochs. Such a bulk could host laboratories, detectors, and samplers capable of examining an entire planetary system in exquisite detail. And if it were a probe, the external crust of ice and dust would make the perfect disguise, a face indistinguishable from that of a natural comet. Velocity, too, enters his case. At 33 kilometers per second relative to the Sun, Atlas arrives faster than most known interstellar visitors, which tend to cluster in the 20-30 kilometers per second range. The difference might sound modest, but Loeb insists it is telling perhaps a trace of artificial acceleration, a push beyond the limits of natural gravitational slingshots. Then comes trajectory. Retrograde motion is not unusual in itself for bodies from the deep galaxy, but Loeb notes how well this particular orbit suits reconnaissance. Moving against the solar system's grain, Atlas plows into the flux of dust and particles head-on, maximizing its ability to sample material. Its steep inclination ensures visibility from multiple vantage points, aligning almost too perfectly with opportunities for observation. And most provocative of all, the chain of planetary encounters. Mars within telescope range, perihelion at ideal heating, a pass by Earth at a comfortable yet revealing distance, then through Jupiter's magnetosphere where samples may be harvested. Loeb calls this choreography statistically implausible for a random rock. To him, it looks like intention. He draws analogies to our own history. Humanity has already launched emissaries, Voyager, Pioneer, on trajectories designed to harvest as much knowledge as possible before they left the cradle. NASA studies of hypothetical interstellar missions have outlined paths not unlike the one Atlas now follows. What if, he suggests, we are glimpsing not an alien message, but alien reconnaissance, what he terms archaeological astronomy, detecting artifacts of technology, not by signal, but by trajectory, structure, and anomaly. Just as terrestrial archaeologists reconstruct civilizations from pottery shards and ruined walls, astronomers might reconstruct the existence of intelligence from comets that are not comets. Camouflage, in Loeb's telling, is not an obstacle but a feature. Why disguise technology? For ethics, perhaps, to observe without contaminating a younger species. For strategy, certainly, to study without revealing capabilities or origins. Even the ice and organics we have measured could be either genuine relics from an ancient stellar nursery or artificial biomimicry, crafted to fool our instruments. A civilization capable of traversing interstellar gulfs could just as easily manufacture isotopic fingerprints as we now manufacture alloys. Timing also gnaws at him. Atlas arrives just as humanity enters its own technological adolescence, deploying telescopes with unprecedented reach, debating interstellar communication, dreaming of our first outbound probes. Is it coincidence that we receive a visitor now, or is it assessment an ancient civilization's progress report on a fledgling world? The trajectory, rich in dust streams and plasma flows, also positions Atlas to collect samples of solar wind, interplanetary grains, and planetary effluents. For a probe, it would be perfect. Critics counter with familiar refrains. Loeb, they say, courts the exotic too readily, favoring extraordinary explanations over mundane ones. Unusual does not mean artificial. Natural diversity in the universe is vast enough to account for anomalies. Extraordinary claims demand extraordinary evidence, and the evidence, for now, remains ambiguous. But Loeb turns the critique on its head. To exclude artificial origins before evidence is fully weighed, he argues, is itself unscientific, a symptom of anthropocentric bias. Why should we assume we already know the limits of possibility? This philosophy is part of his larger program, what he calls space archaeology. Rather than waiting for obvious beacons, radio signals, lasers, he urges astronomers to search the sky for subtler signatures, trajectories that make too much sense, objects that carry contradictions, materials that tell stories not quite natural. If civilizations hide, their artifacts may not broadcast, but they may betray themselves in their motions, their timing, their composition. The implications are dizzying. Should Atlas prove artificial, it would be the first undeniable evidence that we are not alone. And not only that proof that other minds cross the interstellar gulf, that they watch us even as we struggle to watch them. The questions multiply. Who sent it? Why now? What other probes drift through our system, invisible under cometary skins? Even if the artificial interpretation proves false, Loeb's insistence on considering it performs a function. It forces the scientific community to defend assumptions, to sharpen explanations, to admit where probability ends and dogma begins. For Atlas, as for ʻOumuamua, the most puzzling feature may be what it hasn't shown: the outgassing, the glowing tails, the chemistry one expects as solar heating bites. In its silence, as in the dark forest metaphor, lies both the threat and the wonder. Whether a comet, a capsule, or a camouflage, 3i Atlas demands that we look harder at the night and admit that not everything we see will fit the patterns we expect. The silence of 3i Atlas is, in many ways, louder than any signal. For a body of its size and confirmed chemistry, astronomers expected a symphony of emissions as it approached the sun, yet none have come. Ordinary comets, born in the outer reaches of our system, carry a mixture of volatile ices, water, carbon dioxide, methane, ammonia. As they close to within 5 or 6 astronomical units of the sun, solar heat stirs these volatiles, driving them into space and creating the spectacular comet and tails that have entranced human eyes for millennia. Among the very first gases to betray themselves are cyanogen, Cn, and diatomic carbon, C2, molecules that shine in visible light when excited by solar ultraviolet. These are so reliable that their spectral fingerprints have become the canonical test for cometary activation. By late August 2025, Atlas had fallen to 2.5 AU, a distance at which its volatile inventory should have been restless. Infrared spectroscopy had already confirmed the presence of water ice, an accessible reservoir of material primed for sublimation. Sensitive instruments should have caught the telltale CN and C2 lines by now. Yet from the very large telescope in Chile to the twin Keck observatories in Hawaii, the result was the same: silence. Night after night, spectrum after spectrum, the bands remained dark. Even Hubble, above the murk of Earth's atmosphere, staring with ultraviolet eyes sharpened for precisely this hunt, reported nothing. Several explanations circle the mystery. The first is almost banal. Perhaps Atlas has not yet awakened. Some comets remain dormant until they are closer than 2 AU, their surfaces armored by insulating crusts baked hard from repeated perihelia. But this reasoning falters with Atlas. Unlike our local comets, it is no veteran of stellar flybys. Its skin should be pristine, fragile, reactive. It should not be reluctant to sublimate, it should erupt. A second line of thought points to composition. Atlas was not made here. Its nursery lay around a different star, with different chemistry, different pressures, different metallicity. The isotopes already measured in its water-deuterium ratios, unlike anything in our system, hint at fundamental divergence. Perhaps its carbon and nitrogen-bearing molecules abound differently, or exist in ratios alien to our catalogues. If so, its emissions might fall outside the expected bands, shifted or muted, eluding instruments tuned to the familiar. Some researchers stretch further. What if Atlas's organics are locked in molecular architectures we do not encounter locally? If its hydrocarbons or polymers resist disintegration, they may never fragment into the simple diatomic gases that blaze in ordinary cometary spectra. In such a case, heating might not produce chaos, but discipline orderly sublimation, controlled releases, emission lines conspicuous by their absence. It is here that the whispers of camouflage grow loud. If Atlas is not merely natural, if it is a construct cloaked in ice, then perhaps its silence is intentional. A probe disguised as a comet would anticipate spectroscopic scrutiny. Its creators might design sublimation to be selective, releasing just enough water vapor, just enough methane, to look convincing while suppressing the more complex, revealing molecules. A shell 7 miles wide could hide elaborate machinery, systems to vent, systems to mask, systems to decide when and what to reveal. The timing of perihelion, hidden on the sun's far side from Earth, would provide the perfect curtain for such controlled performances. Another possibility lies in the long journey itself. Interstellar space is not empty. It is a thin haze of dust, ions, and relentless cosmic rays. Over millions of years, those particles could have etched Atlas's surface, breaking bonds, reshaping chemistry, welding crusts of exotic compounds atop its ices. The result might be an object superficially comet-like, but fundamentally altered, unresponsive to the sun in ways that make our expectations useless. Radiation hardening could cloak volatiles beneath inert layers, delaying or muting their release. For now, the mystery remains unresolved. The lack of CN and C2 does not prove artificiality, nor does it rule out natural explanations, but it does sharpen the stakes. If emissions appear later, perhaps near perihelion, astronomers will have a baseline, the delayed activation of an unusually insulated interstellar comet. If they never appear, if Atlas glides sunward without ever speaking the spectral language of comets, then we will face a harder question. Did we encounter a chemical stranger, forged in a distant disk under unfamiliar conditions? Or did we glimpse, however briefly, the discipline of design, an emissary, silent by choice, hiding behind a mask of ice? The countdown to perihelion becomes not only a question of heat and light, but of truth. In the coming weeks, The sky will decide whether Atlas wakes as a comet or refuses, and leaves us with silence as its only signature. As 3I Atlas closes in on the Sun, the drama sharpens. By late September 2025, when it reaches 2 astronomical units, astronomers expect the long-awaited transformation to begin. If it is a comet in truth, then gas and dust should pour forth, creating the glowing shroud of a coma and the streaming tail that have always announced a comet's passage. By perihelion in late October, just 1.36 AU from the Sun's solar heat will be merciless, powerful enough to drive even the most reluctant volatiles into space. Should Atlas remain silent then, resisting the Sun's command, it would mark an unprecedented break with everything we know of cometary science. The world's instruments are poised for that moment. The James Webb Space Telescope, its mirrors tuned to the faintest whispers of infrared light, has reserved blocks of precious time. It will search for the tiniest hints of gas, the signatures of molecules escaping into space. Radio observatories are primed as well, listening for molecular transitions invisible to the human eye. Perihelion will be the crucible. If emissions appear, the mystery bends toward the natural. If they do not, the anomaly deepens. Yet even confirmation of ordinary cometary behavior might not be final. In the darkest scenarios, an artificial object could deliberately mimic such activity, releasing volatiles at carefully chosen times to sustain its disguise. For most astronomers, however, the consensus remains anchored in caution and experience. The vast majority believe Atlas is natural, if unusual, and they invoke a principle older than modern science itself: Occam's razor. Extraordinary claims demand extraordinary evidence. To explain Atlas as a machine requires assumptions stacked high advanced civilizations, interstellar probes, camouflage strategies, while natural explanations rely only on processes we know exist. Large bodies can be ejected from planetary systems by giant planets. Pristine chemistry can be preserved over millions of years in interstellar cold. Improbable orbits must occasionally happen in a galaxy of hundreds of billions of stars. To accept artificiality, they argue, is to leap beyond what the data requires. Dr. Alan Fitzsimmons of Queen's University Belfast speaks for this mainstream. In his assessment, Atlas's features, while remarkable, fall within the boundaries of known phenomena. Yes, its scale dwarfs ʻOumuamua and Borisov, but comets like Hale-Bopp or Chariklo prove that such dimensions are not unprecedented. Its water, ice, and organics align exactly with what theory predicts for objects formed in the frozen outskirts of alien planetary systems. Simulations of planet formation, run countless times on supercomputers, produce bodies with precisely these characteristics: large, low density, volatile, rich, and chemically pristine. Even its much-debated trajectory, to which so much intrigue has been attached, can be explained without invoking intent. Dr. Marco Micheli of the European Space Agency notes that improbable is not impossible. In a galaxy with uncountable orbits and interactions, the unlikely must sometimes occur. What's more, human bias distorts perception. We notice, track, and celebrate objects that pass near Earth, or align for easy observation, making their paths seem uncanny. Countless others slip by unseen. What looks like choreography may be no more than the accidents we happen to see. The missing cometary signatures, too, have their defenders in natural models. Dr. Geraint Jones of the Mullard Space Science Laboratory reminds us that comets vary widely. Some remain inert until nearly kissing the Sun, depending on their composition and the depth of crusts that insulate their interiors. In fact, the interstellar age of Atlas may make late awakening more likely, not less. Millions of years adrift in the galaxy expose such objects to cosmic rays and dust, altering their surfaces. Hard layers may form, shielding the volatile interior until intense heat finally overwhelms the barrier. Delayed activity, then, might be exactly what we should expect. And there is the chemistry. Atlas carries water, ice, and organics with isotopic signatures clearly distinct from our own systems. To mainstream astronomers, this is evidence of authenticity. Why, they ask, would a probe's builders bother to engineer such precision? To create convincing isotopic fingerprints would require extraordinary sophistication, far beyond mere disguise. Would it not be simpler for an artificial machine to cloak itself in generic materials, or to avoid detection altogether? Instead, Atlas appears exactly as one would expect of a natural fragment from another star, different, but in ways consistent with theoretical models of chemical diversity across the galaxy. The tension is stark. For the speculative, Atlas is a cipher, its silence a potential mask. For the mainstream, it is a natural wonder, a rare but predictable gift of the cosmos. In late October, the Sun itself will adjudicate. If Atlas erupts with the light of a comet, it will vindicate the cautious and confirm our theories. If it does not, or if it reveals something stranger still, then even the most skeptical may be forced to reconsider what kinds of visitors travel the darkness between stars. Variations in stellar birthplaces inevitably shape the matter they leave behind. Different metallicities, different stellar ages, different histories of nucleosynthesis all weave unique isotopic fingerprints into the ices and rocks of their planets and comets. In this sense, the peculiar isotopic ratios of 318 LAS are not shocking at all. They match predictions for bodies forged under alien conditions, around suns unlike our own. Dr. Aurélie Gilbert-Lepoutre of the Laboratoire de Géologie de Lyon has emphasized that such interstellar visitors provide stress tests for our models of planetary formation. Each one carries the physics and chemistry of another world, pushing our theories of how disks condense, how volatiles freeze, and how systems evolve. With every object that wanders into our skies, we refine our map of how planets emerge across the galaxy. The debate over 3I Atlas has been sharpened by the scientific method itself. Its unusual size, its silent approach, its improbably elegant trajectory all invite speculation about artificiality. But extraordinary claims demand extraordinary evidence, and while Atlas has unsettled many assumptions, none of its traits yet resist explanation through natural processes. The burden lies on those who see a machine cloaked in ice to provide testable predictions, observations that cannot be reconciled with physics alone. Without such falsifiability, theories of hidden technology remain beyond the pale of empirical science. The peer review process has been merciless and essential. Papers analyzing anomalies in Atlas have been published, debated, and dissected. Some scientists have allowed themselves to whisper about camouflage and mimicry, yet the mainstream, guided by decades of studying comets and asteroids, consistently finds natural explanations more compelling. This consensus, critics argue, shows conservatism, but defenders respond that it is the product of experience, the accumulated judgment of astronomers who have seen mysteries before, only to watch them yield to natural law. Public fascination with alien visitors has value. It fuels curiosity, inspires questions, and drives young minds towards science. Dr. Michelle Bannister of the University of Canterbury has noted that such speculation, though intoxicating, must always be weighed against the discipline of evidence. History offers sharp lessons. Pulsars, when first detected as regular radio pulses in the 1960 seconds, were briefly labeled LGM little green men before revealing themselves as neutron stars spinning at dizzying speeds. Gamma-ray bursts, once feared as artificial detonations, turned out to be the death throes of collapsing stars. Again and again, astronomy has shown that the cosmos can create strangeness more profound than imagination without recourse to intelligence. Still, caution does not mean closure. Mainstream astronomers readily admit that their models do not yet answer all the puzzles of Atlas. Its bulk is extraordinary, its isotopes unusual, its silence puzzling. The absence of early cometary emissions remains unexplained, though not unprecedented. These gaps are not endorsements of alien probes, but markers of the frontier places where our understanding is still incomplete, where theory must evolve. Science advances not through leaps to extraordinary claims, but through steady accumulation, through the refinement of models until they fit reality more closely. Perihelion will be decisive. As the sun's heat intensifies, Atlas must either conform to expectations, erupting with the gases of a comet, or persist in silence, forcing astronomers to stretch their frameworks further. The community is prepared for both. Skepticism will remain, but so too will openness, because in anomalies lie discoveries. This tension between imagination and restraint is not new. It has shadowed every great mystery of the sky. The memory of ʻOumuamua, our first interstellar visitor, remains instructive. On the 19th of October 2017, astronomer Robert Werrick spotted it with the Pan-STARRS telescope in Hawaii. At first, it seemed mundane, a faint asteroid crossing near Earth. But tracking quickly revealed the impossible, a hyperbolic trajectory, a body born beyond the solar system. Its name, ʻOumuamua, a messenger from afar arriving first, proved prophetic. ʻOumuamua broke our categories. Photometry revealed a body elongated beyond precedent, 10 times longer than it was wide, a cosmic needle where we expected spheres. Its surface gleamed with an albedo tenfold brighter than typical comets, mirror-like, tinted red. Most spacefaring rocks darken with age, coated by carbon soot from cosmic radiation. ʻOumuamua was inexplicably bright, as though freshly polished. Most confounding of all, it showed no coma, no tail, no whisper of gas. As it neared the sun, instruments strained for evidence of outgassing. None came. Yet its path betrayed a subtle push, a non-gravitational acceleration, as though some hidden pressure propelled it. No cometary emissions explained it. For some, this was the smoking gun. For most, it was a puzzle in need of better models. And so, with Atlas, we stand again at the threshold of mystery. It is larger, darker, and stranger still, but the questions are familiar. Is it comet or construct, relic or probe? The mainstream leans toward nature, fortified by Occam's razor and humbled by history. But the silence of its chemistry, the precision of its orbit, the timing of its arrival, all ensure that speculation persists. Between skepticism and wonder, between evidence and imagination, science threads its careful path. The enigma of ʻOumuamua crystallized around a single, subtle force, an acceleration too precise, too persistent to ignore. As it slipped away from the sun, astronomers noticed that it was not moving exactly as gravity alone demanded. The effect was tiny, on the order of 5 millionths of a meter per second squared, but it was real, above the noise, repeatable across multiple observatories. Dr. Marco Micheli and his team at ESA's Space Situational Awareness Program painstakingly teased it out of positional data, and in June 2018, Nature published the results. The anomaly had become fact. The acceleration fit a clean mathematical curve. It declined with distance from the sun exactly as radiation pressure would predict. And yet, For an object of Oumuamua's estimated size and mass, solar photons should not have had enough leverage to push it so forcefully. The absence of cometary outgassing made the puzzle sharper. Sublimation could have provided thrust, as it does for natural comets, but no tail, no coma, no gas emissions were detected. The universe had presented a riddle that conformed to physics equations while defying its expectations. The mainstream responded with a flurry of natural hypotheses. One suggestion: perhaps subtle outgassing was occurring invisibly, with hydrogen seeping from water ice, a ghostly exhaust too faint for our instruments to see. Others proposed exotic compositions, solid hydrogen icebergs formed in the coldest reaches of interstellar clouds, or unusual blends of organics and volatiles with strange thermal behaviors. Dr. Darrell Seligman and colleagues developed the dark comet model, imagining an object stripped of most volatiles in past stellar flybys, yet retaining just enough to release tiny jets under solar heating. This could reconcile the absence of a visible coma with the presence of measurable thrust, though it required a complex evolutionary history for a traveler from so far away. Into this debate stepped Avi Loeb and Shmuel Bialy with the most radical idea. Oumuamua was not a rock at all, but a light sail. Its extreme elongation, its unusual brightness, and the acceleration curve could all be explained by a wafer-thin sheet reflecting sunlight technology rather than geology. Radiation pressure could propel such a sail across interstellar distances without fuel. To Loeb, the anomalies aligned too neatly with engineering to be dismissed. His argument, published with careful mathematics, ignited controversy. The reaction was swift. Critics pointed to Occam's razor: better to multiply hypotheses of natural composition than to leap to alien technology. Extraordinary claims demand extraordinary evidence, and in this case, evidence seemed thin. Yet the debate could not be silenced. The light sail idea had explanatory power, and in a field driven by data more than philosophy, it demanded consideration, if only to be disproved. NASA's Spitzer Space Telescope provided a crucial constraint. As Oumuamua fled the solar system, Spitzer scanned in the infrared, searching for thermal emission. It found nothing. This non-detection implied the object was smaller and cooler than expected. For conventional models, this added difficulty. A small, highly reflective body with unusual acceleration was harder to reconcile with ordinary rock or ice. For Loeb, it lent fuel to the sail hypothesis. A thin, reflective sheet could indeed be both faint and elusive in the infrared. And then it was gone. Beyond the reach of telescopes, Oumuamua carried its secrets into the dark. What remained was not certainty, but precedent. Its passage showed how limited our observational windows can be for interstellar visitors. A few weeks of data, a cascade of questions, and then silence. Yet in those weeks, astronomy advanced. Protocols were revised, telescopes coordinated, theoretical frameworks expanded. By the time the next visitor came, 2 divided by Borisov in 2019, and now 3. Atlas scientists were ready with sharper instruments and faster response. The lessons of Oumuamua continue to guide the debate over Atlas. First, interstellar objects can and do confound expectations without requiring artificiality. Second, the absence of expected phenomena, no tail, no gas, no dust, can be as significant as their presence. Third, statistical improbabilities must be weighed carefully, accounting for observational bias and chance. Above all, the case showed the value of keeping multiple hypotheses alive. Most favored natural origins, but the discussion of alternatives forced deeper scrutiny, revealing details that might otherwise have been overlooked. ʻOumuamua reminded us of humility. Its elongated shape, reflective skin, anomalous acceleration none had been predicted by theory. Nature, once again, proved stranger than our imagination. As 3I Atlas now approaches perihelion, scientists balance this memory against the fresh anomalies it presents. Perhaps it too will eventually fold into the natural order of comets. Or perhaps, as Loeb and others urge, it will demand that we stretch our imaginations into realms we have so far only dared to whisper about. The legacy of Oumuamua is not only the mystery it left unsolved, but the tools it forced us to build. In its wake, astronomers refined astrometric precision, sharpened spectroscopic methods, and crafted better theoretical scaffolding for understanding bodies from beyond the Sunday. Perhaps more importantly, it taught us how to cooperate at speed. International networks of observatories, rapid data-sharing pipelines, and coordinated analysis teams, all of which now turn their focus toward 3I Atlas. This time, we are ready. Whatever Atlas proves to be natural relic or engineered visitor, the infrastructure forged during the first encounter ensures no photon will be wasted, no anomaly overlooked. Oumuamua's fleeting arc also sparked ambition. For the first time, scientists seriously entertained the audacious idea of chasing down an interstellar object with spacecraft. From this seed grew Project Lyra, a bold proposal by ESA's Advanced Concepts team with collaborators across the world. Its goal, to catch Oumuamua itself, intercept it, and look directly at the first messenger from the stars. The name came from Lyra, the constellation into which the object's path extended, a nod both poetic and precise. The challenge was monumental. By 2018, Oumuamua was already racing outward at 26 kilometers per second. Matching that velocity with chemical rockets was impossible. Even with the most artful planetary gravity assists, no conventional launch system could muster the energy required. Engineers and visionaries sketched out propulsion systems that barely exist. Vast solar sails unfurled in space, ion thrusters powered by sprawling solar arrays, even speculative nuclear or fusion drives. Of these, solar electric propulsion seemed the most plausible near-term path, trading raw thrust for patience, slowly accelerating a craft over years, even decades, until it built the velocity to chase an interstellar quarry. Dr. Andreas Hein of the Initiative for Interstellar Studies mapped out architectures that might, just might, work. His team showed that with optimistic assumptions, a craft launched in the 2020 seconds could reach Oumuamua around mid-century. By then, though, it would be unimaginably distant, sunlight too faint for solar arrays, communication delays stretching to hours, the object itself barely glowing in the black. Instruments would need to survive decades of radiation and vacuum. Shields would have to absorb the impacts of high-velocity dust grains that could shred a craft, and autonomy would be essential. It would be not just a mission, but the rehearsal for humanity's first true steps toward the interstellar frontier. Though it never left the drawing board, Project Lyra changed the conversation. ESA began including interstellar object missions in its planning documents. NASA's JPL explored propulsion concepts with renewed seriousness. Private companies, newly confident in their abilities, started to imagine how their innovations might one day contribute to star-chasing probes. The dream of intercepting a wanderer from beyond was no longer fiction, it was a question of timing. Now, with 3I Atlas discovered inbound rather than outbound, timing is finally on our side. Unlike Oumuamua, which we noticed only as it fled, Atlas was found with months to spare before perihelion. This advance notice is transformative. Already, Dr. Petra Pokorny of NASA's Goddard Space Flight Center is leading studies on what can be done with the time we have. Could we build and launch a dedicated probe within the narrow window available? Could we ride the momentum of existing rockets, existing ion drives, to stage humanity's first true rendezvous with a traveler from another star? The possibilities are as audacious as they are tantalizing. A mission timed to the Mars flyby could intercept Atlas while it is still relatively quiescent, examining its surface before solar heating transforms it. A later rendezvous, during the Jupiter encounter, might exploit the gas giant's immense gravity well, bending the probe's trajectory for a prolonged dance with the interstellar visitor. The sequence of encounters written into Atlas's path, Mars, Earth's orbital neighborhood, Jupiter offers natural windows of opportunity, each one a stage for an ambitious spacecraft to join the play. This convergence of preparation and chance feels almost scripted. The mysteries of Oumuamua taught us humility, forcing us to admit how little we know and how fast we must learn. Project Lyra taught us ambition, showing that even impossible goals can be outlined, studied, dreamed toward. And 3I, Atlas, vast and silent, arriving on its improbable arc, offers the chance to test both humility and ambition in the crucible of reality. It is no longer just an object in the sky. It is an invitation, one that may determine how and when humanity steps beyond the Sunday. The sheer bulk of 3I Atlas rewrites the script for exploration. Where Oumuamua slipped through too small, too fast, too fleeting to catch, Atlas looms as something else entirely, a target large enough to land upon, massive enough to endure detailed study, and, for the first time, stable enough to support the kind of long-duration surface science we dream of but rarely achieve. 7 miles of icy span transforms mission design from desperate pursuit to genuine opportunity. A spacecraft could deploy landers, even penetrators, to probe beneath its crust. Instruments could drill, sample, and analyze subsurface chemistry untouched for billions of years. Such direct access to alien material would represent the most profound laboratory ever opened to science. The stakes are immense. A single gram of Atlas, studied up close, could yield insights into how planets form around other stars, into how organic compounds are distributed across the galaxy, into whether life's seeds might travel between worlds. A handful of dust collected and returned could tell us if our chemistry is universal or if each stellar nursery writes its own molecular code. The possibility of detecting signs of biology, fossilized or faint, hovers over the discussion like a whisper too daring to say aloud. Unlike the fantasy of chasing Oumuamua decades too late, a mission to Atlas is technically within reach. Its trajectory, though complex, offers conventional launch windows. Travel times would be measured in years, not generations. Ion propulsion, already proven in missions like Dawn, could shepherd a probe into rendezvous. Solar sails, long theorized, might provide endurance for extended observation and perhaps even sample return. The barrier is not physics but willpower and cooperation. No single nation can shoulder the cost and complexity alone. NASA, ESA, JAXA, and other agencies would need to combine expertise, perhaps in partnership with private companies whose agility could accelerate innovation. Ambition defines the timeline. A modest flyby, built quickly with existing hardware, could launch within 2 or 3 years, intercepting Atlas on its outbound arc. A full rendezvous with orbiters, landers, and return capsules would demand longer development but remains feasible while the object still lingers within the solar system's reach. The window is finite. Once Atlas slips outward, the chance will vanish for centuries, perhaps forever. The instruments imagined for such a mission echo past comet and asteroid probes, but with sharper edges. spectrometers to pass trace gases and exotic isotopes, cameras to resolve surface features, searching for fractures, vents, or geometric regularities that might whisper of design, magnetometers to detect fields unnatural in origin, radar sounders to peer beneath the surface, mapping voids or structures that nature would struggle to explain, chemical analyzers to seek compounds alien not just to Earth, but to chemistry itself. The goal is not only to confirm what Atlas is, but to test what it might be. The implications are dual. If Atlas is natural, we will finally hold unaltered matter from another star in our hands, a direct core sample of galactic geology. If Atlas is not, if beneath its black ice hides machine or signal, then it will be the most transformative discovery in the history of our species. Either path changes what it means to be human. For now, mission studies multiply. Lessons from Project Lyra, the failed dream of catching Oumuamua guide planners toward agility, cooperation, and flexible architectures. Even if no spacecraft reaches Atlas, the planning alone drives propulsion research, advances autonomy, and expands the scope of international collaboration. These are technologies we will need not just for comets, but for humanity's first true steps into interstellar space. The urgency is real. The window closes with every mile Atlas drifts sunward and then outward again. Our choice is simple: seize the moment, or watch as the third interstellar visitor fades into the dark, taking its secrets beyond our reach. Placed beside Oumuamua and Borisov, Atlas begins to define a spectrum. Oumuamua, enigmatic, elongated, reflective, accelerating mysteriously, yet silent. Borisov, conventional, a comet with the expected coma and tail, yet subtly different in its isotopes and carbon monoxide content. Atlas, massive, pristine, an ice-bound giant bearing both the signatures of distant chemistry and the puzzles of missing emissions. Together, these three are not just anomalies, but a pattern, the first sketch of what interstellar debris truly looks like. Borisov, discovered on the 30th of August, 2019, by amateur Gennady Borisov, reassured astronomers after the shock of Oumuamua. Here at last was a visitor that behaved as the textbooks predicted: water vapor, carbon monoxide, dust plumes, a radiant tail. Its activity matched models, confirming that pristine comets could indeed survive ejection and travel intact for billions of years. And yet, even Borisov carried whispers of difference. Its carbon monoxide to water ratio was higher than any solar system comet, suggesting it was born in a colder disk where CO could freeze solid. Its isotopic signatures diverged subtly but clearly from ours. Small, only a kilometer across Borisov, was ordinary in form, spherical, spinning every 7 hours, built through accretion like so many of our own. But its chemistry told the truth. Interstellar space delivers both the familiar and the foreign. Now, with Atlas, we see the continuum widen. All three objects carry water, ice, and organics, all three formed in cold outer regions of alien planetary systems. All three bear isotopic ratios distinct from our own. These similarities suggest that icy wanderers are the most common emissaries, flung outward in planetary birth throes and cast adrift across the galaxy. They are the messages the stars send to one another, samples written in ice and dust. And Atlas, larger than both predecessors combined 1,000 times over, is the message written in bold. It is a reminder that interstellar debris is not uniform, that the galaxy may be littered with relics of every shape and size, and that each one carries a story not only of its own origin but of ours, of how worlds form, how matter travels, how civilizations choose to watch or remain unseen. The contrasts among our three interstellar visitors, Oumuamua, Borisov, and now 3 Atlas form a kind of natural experiment, each object carrying a different message from the deep galaxy. Together, they outline both the diversity of interstellar debris and the growing sophistication of our ability to catch it. The sheer disparity in scale is the first and most obvious lesson. ʻOumuamua, a slender shard just 400 meters long, was too small to reveal much beyond its silhouette and acceleration. Borisov, a more conventional comet at 1 kilometer across, carried with it the chemistry of water, ice, carbon monoxide, and organic compounds. And then Atlas arrived, 7 miles wide, 1,000 times the bulk of Borisov, a behemoth in comparison. Such a mass cannot be explained by the gentle scattering that ejects small comets during planetary migrations. It hints instead at violent origins, gravitational upheavals, planetary disruptions, even stellar encounters that hurl giants into the void. Cometary behavior deepens the contrast. Borisov activated early, developing a coma at 6 astronomical units, behaving like a textbook comet lit for the first time. Atlas, though vastly larger and richer in volatiles, has remained eerily still as of late August 2025, even within distances where activity should have been unavoidable. ʻOumuamua, of course, was the outlier of outliers. No coma, no gas, no dust, yet accelerating as if pushed by some invisible hand. Trajectory tells another story. ʻOumuamua slipped through quickly, with no planetary encounters to aid our study. Borisov, though bright and cometary, passed the sun without any choreographed dance through the inner system. Atlas, in contrast, weaves a path that feels deliberate. Mars in October, perihelion behind the sun, Earth's proximity in December, Jupiter's magnetosphere in March. Each encounter offers observational leverage, almost as if designed. Composition, too, divides them. ʻOumuamua's makeup remains a cipher. No emissions meant no chemistry to analyze. Borisov, in contrast, spoke clearly. Water vapor, carbon monoxide, isotopes distinct from ours, proof of a cold, carbon-rich nursery. Atlas appears richer, still pristine water ice, complex organics, isotopic signatures from a star older and more metal-rich than our own. Each one adds a page to the atlas of galactic chemistry, showing that while water and carbon are universal, their balances and ratios tell us where and when a body was born. Thermal behavior has proven equally instructive. ʻOumuamua's heat signature confounded expectations, part of the reason for speculation about exotic ices or engineered sails. Borisov's warmth and sublimation followed the script exactly, reassuring in its predictability. Atlas remains untested. Perihelion will decide whether it burns like a comet or holds its silence against the sun's fire. Even the stories of their discovery reveal progress. ʻOumuamua was nearly missed, only recognized as interstellar after several nights, already on its way out. Borisov, spotted inbound, provided longer study but still too brief a window. Atlas, discovered while approaching, offers the longest baseline yet months to prepare, observe, and debate before it reaches its closest pass. Our tools, sharpened by each encounter, have grown in parallel. Automated surveys now flag the improbable faster, telescopes pivot more quickly, and international networks mobilize with practiced coordination. Taken together, the three form the beginnings of a dataset, small but powerful. Already they suggest that interstellar objects span a vast spectrum: shards, comets, giants, inert, active, anomalous. Some behave exactly as models predict, others demand new frameworks. The sample is too small for robust statistics, yet the variety itself is meaningful. Diversity appears to be the rule, not the exception. And perhaps the most important lesson: uniqueness. each object refuses to be a copy of the last. Oumuamua challenged us with absence, no coma, no tail, no precedent. Borisov reassured us with presence, outgassing, dust, chemistry as expected. Atlas now confronts us with scale and silence larger than anything we have seen, yet inactive where activity should have begun. The universe, it seems, is more inventive than our models, ensuring that each new messenger brings not answers, but fresh questions. This is why Atlas's trajectory resonates so deeply. Its improbable precision, its near-perfect alignments, raise questions not only of astrophysics but of intent, chance or design, nature or artifice. The puzzle remains unsolved, but whether natural fragment or engineered probe, Atlas joins its predecessors in expanding the frontier of mystery. Each visitor rewrites the script, forcing us to confront how little we know and how much more waits, hidden in the dark between stars. The geometry of 3I, Atlas's path, reads like a script written for maximum effect. Mars at dawn, when its atmosphere is best illuminated, perihelion concealed behind the sun, shielded from Earth's direct gaze. Earth itself, brushed at a distance, perfect for observation but harmless to orbits. And finally, Jupiter, approached when the giant's magnetosphere yawns wide and its position favors telescopes at home. Each encounter seems tailored, each alignment too convenient. Yet the very elegance that suggests intent is also what statisticians caution us against, the lure of narrative imposed upon coincidence. An alternate view shifts the focus. Rather than planets, perhaps Atlas is sampling the medium itself. As it plows through the solar system on a retrograde orbit, it maximizes its relative speed against the streams of dust, plasma, and charged particles that pervade interplanetary space. To an instrumented probe, this would be a harvest, collecting chemistry, mapping fields, tasting the flavors of a star system. Its trajectory bends at each planetary pass, not to visit but to fine-tune, gravity sculpting the path with billiards-like precision. To plan such a journey would require foresight and mastery of orbital dynamics. But critics remind us, improbable does not mean impossible. Out of billions of possible paths, some will look uncanny. The heart of the debate lies in our own expectations. We assume that an advanced intelligence, if it exists, would optimize as we optimize, choosing efficiency, stealth, and geometry. Yet what if alien priorities differ? What if optimal to us is irrelevant to them? To project our logic onto an intelligence older, stranger, or simply other, risks building mirages. Statistical improbability alone cannot resolve the question. Proof would require direct evidence, a hollow chamber revealed by radar, a magnetic field patterned by circuits, a plume of compounds no comet could produce. Short of that, we are left with shadows and inference. Still, the very act of running these probability models marks a shift in the philosophy of SETI. For 6 decades, the search focused on beacons, radio waves, optical pulses, deliberate signals flung across the void. But Atlas reminds us that intelligence might prefer silence. Reconnaissance probes, if they exist, would cloak themselves as natural, whispering instead of shouting. Detection, then, would mean recognizing subtle deviations in what seems ordinary. Dr. Jill Tarter, who once directed the SETI Institute, has acknowledged that Atlas forces a widening of scope. If advanced civilizations choose stealth, then our surveys must expand from listening for signals to scrutinizing objects. We must learn to read not only radiostatic but orbital mechanics, spectroscopic fingerprints, and the choreography of celestial paths. This demands infrastructure. The Catalina Sky Survey and Linear were built to guard against asteroids, not to chart interstellar visitors. They caught ʻOumuamua, Borisov, and Atlas almost by accident. Robert Werrick, who discovered Oumuamua, has called for dedicated systems, telescopes optimized to spot hyperbolic trajectories, algorithms tuned to flag anomalies, networks designed to detect wanderers long before they sweep past. The Vera C. Rubin Observatory is poised to help. Its large synoptic survey telescope will sweep the sky every few nights, assembling a time-lapse atlas of the cosmos. For the first time, we may catch visitors while they are still in the outer system, with months or years to prepare. Early detection means not just longer study, but the possibility of interception. Spacecraft launched in time to meet, sample, and decide. Yet with capability comes responsibility. SETI has always lived under a tension between openness and caution. To speculate too freely invites ridicule, undermining credibility. To remain too conservative risks blindness, ignoring what may be genuine signs of other minds. Atlas embodies this tension. Its path is improbable enough to provoke whispers, but still explainable by chance. Its silence is anomalous, but not definitive. It sits at the knife edge of interpretation, forcing us to ask what kind of evidence would truly suffice. Whether Atlas proves natural or artificial, it has already expanded the boundary of the possible. It has forced SETI to consider reconnaissance as well as communication, stealth as well as signal. It has made us rethink what contact might look like, not a beacon, not a voice in the void, but a body of ice and rock moving just so, as though watching. And in doing so, it has taught us that the search for intelligence may not be about waiting for a message at all, but about noticing when the patterns of nature lean too close to purpose to be ignored. Seth Shostak of the SETI Institute insists that our response to anomalies like 3I Atlas must be grounded in both openness and rigor. Transparency is vital, he argues. The data must be shared, the interpretations debated, but transparency cannot come at the cost of discipline. The line between what is observed and what is speculated must remain sharp, or the very credibility of the enterprise will erode. For radio signals, SETI has long had protocols, independent confirmation, peer review, and a hierarchy of verification before any public announcement. Now, with interstellar objects stirring whispers of technology, the same standards must be extended to the physical realm. The International Astronomical Union has already begun sketching frameworks for classification, urging systematic observation and collaborative analysis that minimize the sway of bias or hope. The goal is clear criteria so that when extraordinary claims arise, they are tethered to extraordinary evidence. But Atlas also forces a more unsettling reckoning. For decades, SETI prepared us for a distant kind of contact radio whispers from stars 1,000 light-years away, signals safe in their remoteness, time buffered for reflection. An object within our solar system is different. It implies proximity, attention, perhaps surveillance. The sociological weight is heavier. Radio signals do not alter our sky or orbit. A probe, if probe it is, suggests intent. Dr. Douglas Vaycock of METI International warns that humanity is underprepared for such a scenario. We have spent years rehearsing how we might decode a broadcast. We have not rehearsed how to respond if the broadcast turns out to be a machine gliding silently past Mars and Jupiter. Governments and institutions, too, are unready. Existing SETI protocols assume communication, not visitation. Yet, 3I Atlas underscores the need for frameworks that cover every possibility, from the benign to the immediate. NASA's Planetary Defense Coordination Office, originally tasked with scanning for hazardous asteroids, has already broadened its scope to include interstellar objects. The remit has evolved, from rocks that might hit us to wanderers that might watch us, a subtle but profound shift acknowledging that some of these objects may warrant more than orbital tracking. What would confirmation of artificial origin mean? It would not be another scientific milestone, but the milestone, the single most transformative discovery in human history, proof of intelligence beyond Earth, proof of interstellar travel, proof that we were deemed worthy of study. The implications would echo into philosophy, religion, geopolitics, and every layer of human culture. Yet the bar for proof must be set almost impossibly high. History is crowded with mirages, the canals of Mars, mistaken for engineering, pulsars, dubbed LGM, before proving to be neutron stars, ambiguous biosignatures that faded under scrutiny. The cosmos has fooled us before, and may again. So Atlas remains ambiguous. Its trajectory feels choreographed, its perihelion timing uncanny, its silence anomalous. And yet it has not betrayed the telltale signs: no geometric cavities, no engineered compounds, no deviations from gravity's grip. It hovers in that liminal space where probability brushes against imagination. If natural, it is the most remarkable coincidence we have yet seen. If not, it is contact through stealth, the dark forest's watchers gliding past, recording, then departing. Already, its impact on SETI is profound. It has expanded the scope of what we consider evidence, reminding us that intelligence may manifest not in beacons but in subtleties, an orbit too precise, a silence too prolonged. It has shown that interstellar visitors can be caught with the tools we have, and that anomalies can be dissected with statistical precision. It has pulled SETI into collaboration with orbital dynamicists, chemists, material scientists, planetary geologists, disciplines beyond radio astronomy. This interdisciplinary approach may be what prepares us, finally, to recognize intelligence when it no longer hides. And so 3i Atlas departs as it arrived, enigmatic. It bears all the hallmarks of the dark forest theory: 1,000-to-1 trajectory, pristine ice from an ancient star, flybys that read like reconnaissance. Yet it stops just short of revelation. As it completes its passage and fades into interstellar dark, it leaves behind no answers, only the sharpest of questions. Are we witnessing first contact? Or are we simply witnessing the universe, in its vast indifference, dealing us the most exquisite coincidence in human history?